Are there any questions on the quiz? Any questions? Also, I know some taking a quiz again. Laptops. It's what to make a rule not to have laptops. Not have a laptop.
Oh, laptop.
Yeah.
Okay.
Oh yeah, we were talking about let's talk a little bit about independence, okay? And, actually, and then I want to mention central limit theorem. Central limit theorem is why you're in this class. That's why you're in this stat class. So you should. I always tell my elementary classes, if they can't blame the stat class on me, go to their advisor, they have to blame on the central limit. So we should talk a little about it. Now this is a joint distribution. It's sort of a dumb experiment, but we spin a spinner through twice. And it's a fair spinner, and the numbers 1, 2, 3 are minus. And x is a sum, and y is the absolute difference. And then these are all 9 possibilities. And they should all be equally likely because it's a fair spinner. So they all have a probability of 1. And then, like if a 2, 3 is spun, then x is 5. And y is the absolute difference. So it's 1. And what's in this table, that's the joint distribution. And just click on one of these. This 2 9s is the probability that x is 3, right? And y is 1. Okay, and that's true for each of these, right? 0 is the probability x is 6, and y is 1. So that's a joint distribution. Then how about when x is equal to 2? Well, y could be 0, 1, 2, right? 0. But if you add these probabilities up, that's the probability x is 2, 3, 4, 5, and 6, right? That non-shaped distribution. And the probability y is 0, you just add these up. So it's 3 minus. And then y to 1 is 4 minus, and y to 2 is 2 minus. Now, I want to talk about independence, and I think the easiest way to get into it is actually talk about its negative dependence. And we talk a little bit about conditional probability. I can motivate, right? How about a simple motivation problem? Say you have a deck of 52 cards and a well shuffled, and what's the probability the second card is an ace? I'm going to draw cards. With the place. Actually, is that? This is a simple problem, but maybe it makes you think about dependence and independence a little bit. If I had first card there, it would be no hesitation. I score out the 2. Well, how about the second? It's probably the second place.
It's 3 out of 51 times the probability that you drew the ace in the first one, plus the remaining probability times 4 out of 51.
Yeah, you actually, I think you probably took that might even be the right answer. What's the quick answer? What's the right answer? It can only be one number. And usually what I get when I ask this question, I just get these what are conditional probabilities. Here's some probabilities that are simple. Okay, if the first card's an ace, then there's 3 aces as well. And just 51 cards. And this is called given. This bar is pronounced given, it's never pronounced bar. There's 51 cards left in this place. And those are conditional probabilities. So your mind actually thinks in conditional probabilities on this problem. To me, those are probabilities that are easy to get. What is a conditional probability? If you have 2 events, the conditional probability would be given. Well, again, in this problem, these things are easy to get, but how about in general? All right. Well, and why am I even thinking about this? Right. Well, I claim that A and B are independent, then the probability of B given A should just be the probability of B. Knowledge of A does not change the prediction of B. Okay? That's independence. Right. So when I'm done with this little definition, I should have a definition of independence. Knowledge does not change the prediction of B. So that's a way of backing into independence. But then, what does B given A mean? Well, that means that I want to know the chances that B occurs when I know that A has occurred. And A has come up. And with the relative frequency idea of probability, it's easy to come up with the rule. Okay? The relative frequency idea of probability is you have events and you want to know the probability. Well, you just do the trial over and over again, and you just count the number of times that occurs. Okay? And then divide that by your capital N. And capital N is large, then that should be close to the probability rate. So this is the relative frequency. Actually, a lot of large numbers. But for this class, just think of that. Capital N is very large. Right. Now I can get the probability to give me. It's easy. I just do the experiment. If A comes up, I look and see if B came up. And if A doesn't come up, I do the experiment. Here's my little algorithm for the probability of B given A. I do the experiment. If A comes up, I see if B came up. If not, if A does not come up, I should say that. And you just go back and do one. I mean, you go back and do this. And I claim the probability B given A is the number of times I see this divided by the number of times A comes up. Right, that would be depth distribution probability B given A. I just count the number of times that B comes up when I observe A come up. And then I just divide that by the number of times A comes up. Right? That would be the relative frequency. Right? So B might not come up. It won't be in this term. That makes sense, right? That's just the frequency interpretation of conditional probability, right? And then you can answer everything. You can tell me what I counted. What did I actually count? What am I actually counting? Yeah, right, exactly. The number of times they both occur, right? The number of times A and B occurs. then I'm done. And I have my definition. Now, if this was an elementary class, we could work on condition. And we, what's the next theorem? What's the next? Phase theorem. This is not an elementary stat class, and all I want out of it is the definition of independence. Well, A and B will be independent if the probability B given A is the probability B, and that would mean that the probability of A and B would be the product of the probability. And that's actually taken as a definition of conditional of independence because you don't want to worry about this conditional thing. A must occur, so you don't want to get into worrying about the reading by zero. So usually this is just taken as a definition of independence. Okay. Now with conditional probability, you can go back and answer that ACE problem if you want to. Well, I have to draw one picture. Although we could do it with the tree diagram and then don't have to draw one. Okay? So before we do anything, let's solve this problem so we can teach people where this. When I talk about this problem in an elementary class, I always get these probabilities. So people want to think of the conditional probabilities. Then you can solve this problem with tree diagram. Tree diagram, if you have something that goes step by step, like this problem, I draw the first card, then I draw the second card, etc. And each step can be like a section of the tree. So this is set up for it. So you just start at a node, and then this would be the first card. Is what? Well, all you worry about is an ace because then you know the conditional probabilities. So on the first step, you use the ace. Don't you? The probability you get an ace is 4 out of 52, and the probability you don't is 40. Okay? So there's the first card. See, it's a section of the tree. And the second card is the next section. Right? So on the next card, I can do an ace. And then the probability going up here, well, I have 51 cards left, and I have 3 aces. The probability going down here, I have 51 cards left. And 48 of them are not aces. then I can do the same thing here. So this would be, right. Any questions on that? See, those are conditional probabilities that you would do without the concept whatsoever. They're very important. Well, then what's the probability of getting up to this range? Well, it's 3 out of 51 of 4 out of 52. Right? You just multiply these two probabilities together. The chances you go up here are 3 out of 51 times 4 out of 52. And the probability you get down here is 48 out of 51 times 4 out of 52. So you just think that one. You either go up or you go down. Okay. So the chances you get to this node are 4 out of 52 times 3 out of 51. 4 out of 52 times you come up here, and of those times, 3 out of 51 times you get to this. And now the puzzle is almost solved. And the chances of getting out the answer are almost gone. Second card's an ace is here, or here, and those are disjoint events. Okay, I can't. All the nodes are disjoint. You can't be on the same. You can't be on two nodes at the same time. So those are disjoint events. Okay, and this event gave me an ace on the second card, and this event gave me an ace on the second card. So I just have to add those two together, and I have the answer. The answer is done. The probability of the second card is an ace. Now don't compute that, just factor out. It's over. It's 4 out of 52. What else could it be? You give me another answer, I come back and say you stacked it. You stacked the deck. There's nothing special about the second card any more than there is about the first. Now you can make a big jump. What's the probability that the second card is an ace? So you're not looking backwards at all. You're just asking a question. Okay. Any questions on that? That's how you bet in poker, right? You have playing poker with people, and you each have 5 cards, and you say you're playing draw poker. So you have to throw 3 cards in, and you get 3 numbers. You find all those probabilities of why you're doing that with your hand on. Even though there are 6 people playing, you can't worry about what they have. You think, well, the deck is them all shuffled. So, probabilities I have to deal with. So, I can threw those 3 cards in. You didn't have any aces in your hand whatsoever. The probability the next card comes to you being an ace is 4 out of 52. You have to reason. I mean, you do some conditional stuff. Okay, then finally getting back to this, these random variables independent, and for the discrete case, independence is easy. Well, not easy, but it will actually be easy to test because you test it exactly the same way in about 2 months, right? See, we could just go back, we could just use the definition of independence for discrete random variables. So for discrete random variables, it's what? You have a joint distribution, and then you have the marginal distributions. They're independent if and only if the marginals, the product of the marginals is equal to the joint. Right? These are clearly dependent. There's no way that's going to happen with this. I have 0. 0 equal to 2 nines times 2 nines. So they're dependent. So these random variables are dependent. And if you think about it, it's easy to see because if I know x comes up 2, y comes up 0, the probability 1. So they're dependent. Okay. And here's a good example, if you want to think of applied quantum, is a hair color quantum, the Scottish school children. These are all, it's almost like a probability distribution because there's so many, I think there are like 3,000 people in this number. And so we got their eye color and their hair color. So 6% of the students had blue eyes and fair hair. 7 years long, there's some really rare ones. Blue eyes and black hair is like 1 out of 1,000. 1 out of 10,000. Yeah, right. So it's really rare. I guess medium is hazel. So, I used to have hair, probably dark. So, about 80% of us. Though not scratch. Mixture in Pittsburgh. Pittsburgh is where Heinz is. Heinz used to have a slogan, I think they still use it once in a while, 57 varieties. That's the parents always give you. You'd ask them, what happens? And say, well, the Heinz 57. The mixture. It's just so true. You're not going to get these. I could laugh here with 0.13 times 12. You can get off this. 0.3 times 0.4 to 0.12 by 0.17. Probably not 3 times. There's another 6. But yeah, I have one.
Well, for like the or with like the fair hair. Now, does blue eyes and medium eyes almost identically?
Blue eyes.
When we use the fair hair and blue eyes and fair hair and
Is 0.06.
fair blue eyes and fair hair and medium eyes are almost the same thing. But blue eyes and medium eyes don't have anything to do with the same.
Yeah, you could pick out sections of the table. Certainly is. Overall. And you know that now. Again, this is a turn of the century, and DNA and methods. Although Mendel had been around, right? Mendel and Darwin were there, but they never got together. I always think that if it was today, we would have DNA much earlier, because Mendel was right on the key. Now, for continuous random variables, it's not that easy, and what we go to is see, we'll be able to test for independence. I mean, we wrote down a definition of independence. We'll be able to test that in the discrete case. In the continuous case, you can't do that. And that's like a bit of a mystery. No, I shouldn't say mystery, but there's people that used to worry about this. If you look at some old papers, you occasionally see someone trying to seek independence for continuous. Trying to get it. In the continuous case, of course, we don't have these. These are all zeros. 0 is equal to 0 times 0. So it's absurd. You're not going to get independence that way. Okay, it's density that has these factors, and that's not easy to test, because then you have to estimate the density. Okay. So in the continuous case, we'll have to look at the parameters. And I think we could just switch. I don't want to be honest. We'll definitely use independence on very intuitively. The statistics we're looking at require independence in the sample. Okay, we'll talk about that. I'll push that all through this class. Okay, in fact, let's the example is random, and I think we've even defined this a few times. If the two conditions hold, the items are independent. Now, another independence means. Even in the continuous case, I mean, the conditional distribution of x given y is independence means that that is a distribution of x. Okay. That's still works. You just can't do like a discrete rule. Next definition, we put some notation to confuse everything. It's 1 through x and 5. So this is independence, and this is again discriminant. And so often we just say the x's are I nature. Now, if you're sampling from a distribution and you have a random sample and the distribution at least has finite variance, then the arithmetic average of your sample, this distribution becomes normal as the sample size goes to infinity. That's the central limit. So let's talk about the central limit and then start with this. This is a random sample. On a distribution. It's mean mu. And variance. Sigma squared, which is 0.9. You can look at S, the sum of the binomial, right? And of course, X bar, the so that's the sample. S is the sample sum, and X bar is the sample. And S is distributed approximately as a normal, and the mean would be n times mu, and the variance is n sigma squared. And X bar is approximately normal between mu and variance sigma squared. That's the key right there, that last thing. You could see it coming if you look at S, because this is n mu, and if you have scale, this is root n times sigma. It's not, you don't have n, you have root n. And then if you look at the variance of X bar, it's just it's sigma squared. So the distribution of X bar is approximately, I always draw a visual line. And its height is shrinking as n goes, it's large. I mean, its height is going to infinity as n gets large. Because you have that 2 pi in here, sigma root n. That goes upstairs. So as n gets large, that goes to infinity. Well, all the mass has to be 1, so then all the mass goes in. And that's what makes statistics work. Without that, you wouldn't be in this class. Of course, you probably wouldn't have a universe either, but so the essential limit theorem says if you add up a bunch of things which are relatively the same, okay, they're independent of one another, and they have the same distribution, and you can relax these some, especially the distribution. The independence, you have to be more careful. So independence we want. But if you add a bunch of things up, then it becomes non-shared. And again, that old spinner problem is still on, right? Because these spins are flat, right? And I add 2 flat distributions together, and I get something that's non-shared. So it's not. But it just doesn't have to be a spinner, it happens for many things. So we use this from time to time, and we can solve it. I know some of you had plans. But I just have to, it's coming. It's the elevator problem, right? Now you can solve the elevator problem, so guess what? You've learned a lot in this class already, right? And here's the elevator problem. 16 adult males approach an elevator on the 100th floor of River Tower. The elevator has a sign, maximum weight is 2,900 pounds. These adults enter the elevator. Find the probability that the cable snaps and they plunge to their death. Okay. Well, then what's this problem? You just want to know if their combined weight exceeds 2,900 pounds. So it's yes, right? Now you know how to solve this problem. So, oh, guess what S is? It's a sum from 1 to 16. These guys' weights. That's the guy's weight of the X guy. I just want to know the problem with S is greater than 20. And you say, all right, I'm taking my parametric stack class and talk about this instrumental. And so I just want to find this area. It'll be approximation. Okay, so in a sense, the problem is solved, right? What else do you need to know? Well, I can make a z-score. So I need a mean, but in this problem, that's easy. We don't even measure everyone's weight every time they go to the doctors. So you're always still building. So we have a good idea what the average weight is. Might have to specify the populations. I'm thinking probably adult males in the 20s. And the average weight's about 170. But you can get this. You can just go out to the web, whatever, or take your favorite database, mine it, and maybe it says means 170, and sigma is 15. Then you're upset because we have 16 items, and so I know the mean of S is just 16 times 170. And the standard deviation is actually root it's 16 times so this is 60. So okay, let me just set it up and well, that's good. So the mean weight is 2720, and I have to give 2900. Oh, yeah, I'll just. And it's just one. We don't have to think of it as a number. So it's one out. So it's not odd for one, if you divide this by 16. If you by sample averages, you need that. It's 181.25. It's not odd for one individual to weigh. So for one individual, it would be, the mean would be 7 deviations. See, that can happen 23% of the time. But it is odd for 16 individuals to have a sample average that exceeds 181 pounds. See, I mean, that's a big difference. Sixteen people, 16 is a subset. It's a big difference. You're starting to use the central limit theorem in odd places like catching cheating in schools, right? It's not odd that one of the fourth graders, but it is odd if we have a lunch. So, we do things intelligently. Okay, any questions on central limit theorem? Okay, so let's go to inference now. We'll just start with the binomial problem, and then the next chapter will be on Thursday. Will be just a one sample discrete problem, and then probably next Tuesday, so one sample 15. Any questions on this? And it's worth talking about because this happens all the time by binomial proportions, right? And even like the sign test we'll talk about is a binomial proportion in a couple of weeks. So it'll come up in non-parametrics. Okay. Now you don't want to think about the binomial problem. That's actually the samples. You just want to think about it when you. There's like one trial. Okay. This is the population. So if it's success, you can take it back if you want to. If it's 1 if it's success, 0 if it's failure. And the probability of success is the binomial proportion. I should really say the moving proportion. And that's the probability of success. So you can table the distribution. We talked about this in the first variance is p times q, and again q is 1 minus q. So this is our population. So now we're back in the statistics finally. We know we have, this is our population, we don't know p, and we know we'll never know p. So the other thing statisticians can do is observe. So we just observe a sample on this. So it's, again, it's like someone turning the crank, and through the wall come these observations, right? They might be very expensive. It might be very expensive to turn them. So you may have a very small sample. Hopefully in this problem it's not that small. So what does this mean? Well, it's a very simple one. It's x of I is 1, it's the i's the trial. Success, and 0 the right triangle. Okay? And P is the unknown, so here's our estimate, right? P have to be the number of successes, right? In trials, but it's just a sample average of the answers, right? Here's, I'll give you a sample. Here's a sample size 50. Really well. So I'm going to generate this. It's from a binomial model. I want 50 items, and it's renewed, okay? And the probability of success is 0.6. So at the top is the left side of the wall, and at the bottom is the right side. That's all you have, okay? Just have this information. Zeros and ones, where 1 is success and 0 is cover. So then, so here's P hat, right? It's just the mean of X. .5. Your estimate's wrong. You missed. Not 0.6, it's 0.5. Okay. And then, of course, the question is, you've got to practice that. Oh, I just need to know the error. The important thing is the error of estimation. So now you want a confidence. So then how do we get a confidence? You can actually get an exact confidence. It's a mess. Usually we don't do it. But as usually fairly large ones, so there's something you don't hesitate on, we'll just run it at central limit, right? P hat is approximately normal. And from that I can get a confidence. You can actually see from the normal distribution. I don't know, see, this is an X bar. Let me just do it in general. I don't want to spend much time on this. But here's the distribution of X bar. Where did you start? It's approximately 1. So you can always start, you get confidence intervals the following way. You start with a percentage, what you have the answer. actually get an idea what a confidence interval is. And I know an answer. I can give you bounds down here where the probability is 95%. Remember, it's the distribution of x bar. So my sigma, I have to cut by root m. And in this class, we can just go to 1.96, right? Right? This would be an approximation. So here's an interval. Okay. And you just ignore sigma for a moment, and you can tell me that's not an interval you could use. Right? So you're trying to estimate mu, like you're trying to estimate p, right? P would be mu in the problem we have. So you're trying to estimate mu, and you come back and say, here's the interval, it's mu minus this to mu plus this, and of course it's defined in terms of mu. But what can you do? What would you do in this problem? It's like we started with a probability and we have an interval, but it's wrong. We can't use mu. So what do? You just put x bar in. It works. The interval will work, right? This interval will work because what's the probability that interval traps mu? Well, this interval has the same length as this interval. Okay.
What is r sub n? Oh, this is square root of n.
I'm sorry. Any more questions? Because this is at a, see, the half length is 1.96 times sigma root n. This is half length. When doesn't the interval, this interval catch mu? Actually, if x bar is down here, you're out of luck. This is half length. If x bar is here, this would be the upper limit. Sorry, you didn't catch it. Okay. And if x bar is up here, half length won't catch it. See, it's here. Sorry, here's the lower bound. You missed. Here's the lower bound, the upper bound. But if x bar is in that 95% band, it catches. Right? Here, it's on the edge. You just got in. But half length does it. The upper bound exceeds the mean. So the interval works 95% of the time. So in our particular problem, the x bar is p hat. But sigma gets root p times q. So there's our interval. There's our 95% confidence. Now, this is 95% confidence, and 0.05 is what's left. 0.025 is the area here, right? So we say 1.96 is z critical value, 0.025. You might want to think of it as z 0.05 too. Now, you've seen this before, so we don't have to spend a lot of time on that. We can get critical values. You know, where do you get the z critical values? That's sort of that stack values. I have to be 99% sure. 95. Some people want off with B1, so I need 2.005. So where do you get those? Don't say there's one and two. What table am I looking for? It's the T table, right? It's the T table 50 and 20. You just pick up those. Now, I didn't do that, so I got I have to do it the hard way. Yes, what, 2.57. So then my confidence number would be that. I'll put all radically, and then of course I don't know P, I have to estimate yet. I just put the estimate. Okay, so there's my confidence interval. Okay, any questions on that? That's like a review on confidence intervals. This is for the binomial proportion. If I change alpha, well, we can go over some. So here I have, this would be a 95% confidence interval, 99%. The Z critical value here is 1.96. Here's 2.57. So my second interval, I've lost precision. I'm not estimating as precise as I was in the first one. See, this one's going to be bigger. It's going to be wide by a substantial margin. That's the price I paid for going from 95% confidence to 99%. Okay, so now, what's 100% confidence interval in this annuity problem? There's one. What's 100% confidence? I'm absolutely sure that P is 1. Well, that would be for mu, but for P, I can't. 0 to 1. So your boss wants to be 100% confident. Oh, that's easy. You don't even have to sample. Now, if yours the one, what's the 0%? Right?
Pick a number.
No.
Any single probability, point there.
Yeah, that's, in a sense that's true, but what's one that's used in practice? You'll run into people who use 0% confidence intervals all the time. What is it? Yeah, P half. That's it. No, we missed. We just saw that we missed, but you're 100% sure that that's the true value. Right? You see people that they get caught up in this. I don't know why. They miss the big picture. Okay, any questions on confidence intervals? We can go back to see if these guys in confidence. Remember, P was 0.6, so our estimate's off. The confidence interval, I like to call the, first of all, our confidence interval is of the form, and a lot of them will be in this class, is P hat, and if you go back to our notation, you can see this. This is just the standard error of P. Well, it's estimate. But the standard error of P is the standard deviation of P hat. Okay, that's population. And the standard error is radical PQ over N. So our confidence interval is of that form, and a lot of them will be, okay? I call this a symmetric confidence interval. So often you, in practice, I'm going to return P hat and the standard error and then the confidence interval. So my standard error will be sample size was 50. So there's my standard error. And you can see now you're going to track. So the upper bound will be let's just do 95%. And the lower bound will be, oops, this is what make that harder. So we change name. And so here's LB. This is a successful confidence interval. They trapped new P. And see, again, in this class, we can't play God. Okay, we can be on the left side of the wall. We can look at our statistics and see how we will do. In this case, we were successful. Okay, we just caught it. You see people using, you'll see this on the media all the time. They will talk about the confidence interval, like the margin of error, and then they go right back to the estimate. You see it all the time. It's obvious from the confidence interval, it's a toss-up. Maybe it's like a poll for two candidates or something. It's a toss-up, zeros in the confidence interval, and but your candidates on on the right side, so they would run right back to the estimate. I've seen that. Over and over. I feel like yelling at them. It's a toss-up. I can't say that. It's inconclusive. But we did get it this time. Any questions on the confidence interval? Oh, again, the last thing on confidence intervals for today is, the confidence interval itself is a Bernoulli trial. Suppose you do 95% confidence intervals the rest of your life. In fact, the government says, in general, unless you have a reason for the contrary, you're going to use 95% confidence intervals, period. Okay? They said that at about it was probably 75 or 76. I can remember the article in the stat we were talking about. Okay? I mean, that was like, it's like the bottom line. Okay, so now you're a good government person, and in this class we're often good government people. Okay? If I don't say that confidence, then always say I'm a good government person. You just do that. But a good government person does 95% confidence. So the probability of success on his Bernoulli trial is 0.95. So if he does 20 confidence intervals, he expects to be wrong once, in general. See, we have this confidence interval, but when we go to the sample and actually add numbers, We just have an interval rate. But the interval is an outcome of a Bernoulli trial, and the probability of success is 0.95. That's where you get the word confidence. So, just keep that in mind. And next time we'll start by looking at a bunch of confidence intervals. So I want to drum home that idea. You can be wrong. You're wrong one side of 20 times. Okay, well, I think we're on our way. I'll sign some more problems. There's no quiz on Thursday. It's going to be testing next.
No quiz on Thursday.
That's what he said.
Okay, I only heard the last